In this class, we discuss about BLDC ceiling fan with the switched inductor curve converter. So, in previous times, for conversion of DC-DC, when we compare to the BTech students, they are preferring boost converter. So, instead of boost converter, I am proposing this paper curve converter. This is a DC-DC converter. So, why we are using these curve converter and what is the role of the curve converter in this paper, I will tell you. And I am proposing BLDC motor. So many people already know regarding to the BLDC motor, brushless DC motor. So I simply go to the model. This is the model. So initially I am having AC supply here. I need to convert AC to DC. I am using two-leg diode bridge rectifier, and then I am proposing the curve converter. In curve converter, we having one MOSFET with the IGBT, MOSFET with the anti-parallel connection of diode. This MOSFET switching frequency is already given here. The switching frequency is 200 kilohertz. So this switch is going to turn on by the pulse mentioned by the switching frequency. And then we getting low DC voltage is converted to the limited DC voltage regarding to the input of the voltage source inverter. And then the output of this voltage source inverter is connected to the BLDC motor. BLDC motor, you already know this is DC device. How this BLDC motor going to work on, I will show you in simulation. So this is the simulation diagram for the proposed design. So output of the BLDC motor, I am connecting feedback terminals. These feedback terminals, that means whatever the performance of the BLDC motor, we need to know. How we are going to know the performance of the BLDC motor means with the help of the sensors. We require sensors. So I am taking Hall sensors are the feedback from this terminal. This is the Hall sensor. So here we having so many parameters regarding to the BLDC. You can use any one of these things regarding to the requirements. You can change anything. Okay. So I just need to take Hall sensors itself. Okay, that's why I'm just connecting this Hall sensor here, and then I'm converting this Hall sensor to decoder to create back EMF. That means to generate which at which time interval I need to uh, generate pulses. Okay, this gonna help you to create at which terminal I need to create pulse means this gonna help. That means the decoder can help that thing. So whatever the EMF can generate, that EMF is going to convert into the pulse. I mean, switching at which time interval I need to switch on and switch off. Those will be depends upon this operation. And then from here we can get the pulses across these S1 to S6 pulses. These pulses is given to the voltage source inverter, and then automatically it will act as a closed loop to check the performance of the BLDs. And we are taking different voltage as a feedback reference signals. I will show you clearly one by one. So in this, I am just taking 15 voltage, and another terminal I am taking 35 as a reference voltage. In base paper, they mentioned already clearly. We need to change the DC voltage references. Regarding to that one, I am changing. Here, they already mentioned different voltages we need to change to observe the performance of the BLDC motor. That is the major role for this design. So for that purpose only, I am just changing the reference voltage to check the performance of the BLDC motor. So I will show you the results of the proposed video design. Uh, First of all, we need to check the steady state performance of the BLDC motor. So this is the waveform to check the steady state performance of the BLDC motor. This one, figure number 5. This is the result for the BLDC motor. Steady state performance means we don't apply any change at the either if you take mechanical torque, it is dynamic response of the BLDC motor. If you take input change voltage means it also considers the dynamic performance. Either you need to change the input or you just need to change the output. Depends upon the changing parameter. Either it will be input or output, it going to change the performance of the system. Okay, so I'm just considering the for the first case like this way, and second case, third case, fourth case, I just showed the results here. Just the valuing will be reference DC voltage itself. Okay, that is, it doesn't having any change at all, only the reference voltage we are changing. I will show you each and every result what we are getting. So I am just considering at here already they mentioned 48 voltage, 35 voltage, 15 voltage. I am just checking with 15 voltage right now. So this is the 15 voltage as reference. We need to consider this one. This is the waveform for that one. In a similar way, we are considering 35 voltage also. Why? Because they mentioning. Okay. Because they mentioning this thing means that's why we just design according to that one. Here also we don't change any dynamic performance. We just consider the reference voltage itself. We don't switch it into the dynamic response. Okay. Presently we are going to the steady response itself. I will tell you where the dynamic performance will going to operate. So at these three cases, I just perform the uh, steady state condition. This one is the steady state results. You just need to check the difference in the various terminals. Okay, that is the major thing. In these outputs, we are taking VDC input, current output, and DC link voltage. And this one is rotor speed, and this one is stator currents. So like this way, you whatever the requirements you need to take up means those results can shown like this way. In this paper, they mention all these things. That's why I just pick those results itself. Okay, and dynamic response. Now I am going to show the dynamic response. That means we need to change the input. That means the voltage we need to switch it into another term. That means from 0 to 0.2, we are entering 220 voltage, and from 0.2 to 0.4, we just step down the voltage. That is the dynamic performance. So when we switch the voltage means there is a variation from here to here. When you observe in this magnitude, the voltage of this magnitude from 0 to 0.2 will be 220. And then when the dynamic performance means we need to switch into another term. That means input we need to change from 220 to here the magnitude will be 100. Okay. So 200 and 2 we are changing the voltage to 100 voltage. So that's why here there is a variation with respect to the input. Okay. So the currents also change with respect to change in the voltage as well as all the parameters, VDC link, rotor speed, and stator currents, all this will be changed with respect to the dynamic state condition. Okay. So in a similar way, we just changing with the 270 voltage. Previously 200 we are mentioning. 200 to 90 voltage previously we are considering. Now we are previous case in previous case we stepped down the voltage. Now we are increasing the voltage 220 to 270. Now we are increasing the voltage. By changing the voltage, we can get the higher magnitude. From here to here, we are having lower magnitude, and from here to here, we having there is an increase in magnitude. You just need to consider. Suppose if you check the magnitude here, there will be definitely a variation. By looking directly without maximizing that waveform, you cannot figure it out the variation between 220 and 270. When you zoom that parameter, you can easily identify the magnitude of these two things. Okay. In a similar way, this is the case of the dynamic performance of the BLDC motor when input change. Suppose if you change step down or step up, the performance of the BLDC motor we going to operate uh, randomly with respect to the inputs. Okay. So this is the uh, overall explanation regarding to the BLDC ceiling fan, which is the switched inductor converter. Okay. Thank you for watching.